Right, let's get on to part two of the talk. Thanks, thanks for coming back. And yeah, so what do we talk about in the first part? We are saying building blocks. Building blocks are cool. We should understand building blocks. Um, we did a little detour into RAM models because it was important. Some algorithms need to use these RAM models, and we talked about some classical paradigms that can be quantized. You can upgrade these classical paradigms to get better quantum paradigms. And one other thing I want to talk about just before I get to classical and quantum primitives is how we access inputs. So we already talked about Grover's algorithm, and it has an interesting way to access the input, right? So maybe let's talk about why am I even talking about these different input types? And so you might say that, like, listen, I only want to solve computational problems that have that are classical, like the input is classical and the output is classical. Like these are the only computational problems I want to solve. But even if that's the kind of computational problem you want to solve, classical input data, classical output data, in the intermediate stages of your algorithm, you might want to go through quantum data. Right? So you might have a problem that starts out with some classical data. You want to output some classical data. But in the middle, you might want to use a primitive that converts the classical data to quantum data. You might want to use another primitive that genuinely natively acts on quantum data, outputs quantum data. And then maybe you want to use a third primitive that takes quantum data and outputs classical data. And you might think, wait, does this actually happen? But this does happen. There are quantum algorithms that ultimately are about classical data, output classical data, but in the middle, you have to, if you want to think about the primitives involved, you will have to go to the abstraction of quantum data. And here's some examples of primitives that have all of these features. So if you want to go from classical data to quantum data, uh, all kinds of quantum state prep algorithms, so quantum algorithms that prepare a quantum state given some kind of classical description of it, would be an example of such a primitive. So if you've these are examples of some quantum state prep primitives that might be useful in quantum algorithm design. Grover Rudolph is a well-known way of making quantum states with certain properties. There's something called quantum rejection sampling. There's also the brute force algorithm, which is just like you can just make any quantum state with some number of gates. In fact, fun fact, did you know you can create an arbitrary quantum state on n qubits using only 2 to the n over n elementary gates? So gates from your finite gate set. This is not it's not a totally obvious statement, and in fact, it was not known until this year. And this talk on Friday will tell you how to do it. The non-trivial part is how do you do it with 2 to the n divided by n elementary gate sets. If you just want to do it with 2 to the n elementary gates, this was already known. It's been known for a very long time. But in fact, you can create an arbitrary state like this. Anyway, fun fact, not really related to what I want to talk about. Right, so then there are primitives that genuinely take quantum data and transform it to other quantum data. One example would be the Hamiltonian simulation problem, which takes some quantum state and does quantum time evolution on it and gives you a new quantum state. There's the quantum linear systems problem. I'll talk about it in a bit. And finally, you can have primitives that take quantum data, like a quantum state, for example, and output some classical data from it. So any kind of like tomography algorithm that you've heard of is generally of this form. So things like shadow tomography, classical shadows. There's some metrology papers at QIP this year, which also are of this format. You're trying to learn some classical data from quantum states. So all I'm trying to say is that even if you only care about classical input, classical output problems, the primitives that you need to understand will also need to have quantum access to data and output quantum states. And the example we saw with Grover's algorithm, for example, said that even if you care about solving problems only in the circuit model, you need to understand black box algorithms, right? Algorithms with query access to the input, like Grover's algorithm, because you can use a black box algorithm and come up with a circuit model algorithm. So I just wanted to spend a few minutes, maybe like 5 minutes, talking about different ways we assume quantum access to different types of data. So we already saw this in the first part of the talk. We saw how you might express query access to classical data. And one way to do this is the same way I described with Grover's algorithm. You have some function, and you have access to this unitary that, on a given input and a bit, it keeps the input the same, and it copies the value of the function. It XORs it over there. And if you remember, this is exactly the same as saying that it's not a classical function, but it's actually just a classical bit string. And it's just the bit string is of length n, which is 2 to the little n. So we already talked about this. It's just a recap of this is one way we think about having access to classical data, like in Grover's algorithm. So yeah, I got this question also in the break between part one and part two, which is why does Grover's algorithm assume access to this kind of OF? Like, why don't we just say that you're given a classical circuit for F with G gates, and that'll give us this OF with ordered G gates, as I said earlier. But that's only one way of instantiating this OF, right? Like, we might also have a quantum algorithm for F. There was also a question about this earlier. And another way to instantiate this OF is like this truth table of F might just be stored in some QRAM, maybe CQRAM or QQRAM or whatever. And all of these cases are covered by Grover's algorithm. So the reason why we state Grover's algorithm is in this generality, and in fact, why we state all black box algorithms in this level of generality, is that the algorithm doesn't actually care how you implemented the black box. It just cares about the input-output behavior of the black box. This is why we assume Grover's algorithm assumes it doesn't specifically list out the ways in which this Oracle OF could be implemented. It just says that OF is the Oracle we have. And these are three examples of why we might have access to this Oracle. There could be more. These are just three that I came up with. Good. So this is query access to classical data. Let me also talk about quantum algorithms that assume access to other quantum algorithms or unitaries. And I'll give you some examples in the second half of this talk. For phase estimation, for example, is an algorithm, if people know, that assumes as input another quantum algorithm. So let's say U is the other quantum algorithm, and you want to have access to it. The most common access model that I've seen is you assume that you're able to apply U, but not just that you're able to apply U, but you can also apply the controlled version of U and the inverse of U. And why might this be a reasonable thing to do? Like, it's because if you had a circuit for U, even if you don't understand what's going on in the circuit's horribly complicated, you don't know what it's doing, you can always mechanically construct from a circuit for U a circuit for controlled U. Just totally mechanically. So you give me a circuit description of U, so that's just a sequence of these elementary gates. I can look at these elementary gates and make a new circuit that does controlled U and U inverse. And how do you do this? It's pretty easy. So for controlled U, you take each of your elementary gates. So elementary gates were Hadamard, T, and C naught. And every time you see a gate, you replace it with its controlled version. So you got your old circuit, it had Hadamard, T, and C naught. You replace it with controlled Hadamard, controlled T, and controlled C naught everywhere. And now you express each of these gates, again, back in terms of the elementary gate set. And you can do this with constant overhead. So if you have an explicit quantum circuit for U, you also have an explicit quantum circuit for controlled U, and its cost is roughly the same. Maybe there's a constant factor blow up. U inverse is even easier. If you have a circuit for U, which is a product of elementary gates, U1 to UG, its inverse is just the same product, but just reversed in order, and you replace each gate with its inverse. So if I have an explicit circuit for U, I can easily construct controlled U, controlled U inverse, controlled U inverse. So it's pretty reasonable to give yourself access to these as well in quantum algorithms. You'll see many algorithms will do this. Phase estimation, for example, assumes access to controlled U. So this is the most common access model for unitaries. Sometimes you'll see an access model that only gives you access to U. This is less common, but but it makes sense if, for example, U is being performed outside of your control, like it's not performed by you on your quantum computer, like maybe another agent. This doesn't occur that frequently in a quantum algorithmic context, but like in some kind of context, like complexity theory, for example, you might have a unitary being performed on your circuit by somebody else. So that's why you might access it, model this access by you, or you might have something that's affecting your quantum computer that's not even a circuit. It's like some, I don't know, like an external magnetic field is acting on your quantum computer, and it's doing some unitary. But you don't have it as a circuit, so you can't do its inverse. But anyway, this is a slightly uncommon model, but just thought I'd mention that. And the last thing I want to mention is quantum access to states. This is many quantum algorithms will also assume quantum access to quantum states. The most common way to do it is just say that the quantum algorithm gets as input copies of the quantum state. So if your quantum state is pure, maybe you just get n copies of ket psi. Or if it's mixed rho, maybe you just get n copies of rho. And these kinds of models are often called sample complexity because the resource you're often trying to minimize is the number of copies of psi or copies of rho. And these are also called samples. So it's like, can I minimize the number of samples? So it's called sample complexity. So many quantum algorithms, if you're familiar with any of these, shadow tomography, classical shadows, full state tomography, they'll generally assume that you have many copies of a quantum state and you want to learn some properties of it. Like in shadow tomography, you want to compute a set of observables. In full state tomography, you want to write down a classical description of this quantum state. So this is quite reasonable. But there's a second model, which sometimes is more powerful, and we'll also see it later on, which is that you don't assume copies of the state, but you assume access to the unitary that prepares the state, starting from some canonical starting state, let's say the all zero state. This is different from the first model because, of course, you can create your state because you can just take the unitary you were given, apply it to the all zero circuit, and get the state. But you can sometimes do more. And in fact, there can be speedups in this model. I'll give some examples later, but here are just some two papers just from the last 2 years that show, like, if you have the state preparation unitary for a circuit, for a state, not just copies of the state, but the unitary that prepares the state, you can solve certain problems faster, like computing expectation values or doing state tomography. Okay, that's just a quick intro to the kinds of access we will assume to objects, because now I'm going to start talking about primitives, and different primitives will use different kind of access models. And yeah, that's all I wanted to say about that. Just a quick side note, really. Let's get back to talking about primitives. So in the first half of the talk, I said we should focus on the building blocks, right? Like, so how you design algorithms is, how you design new algorithms is think about building blocks, think about how these building blocks fit together. And one of the things I said was it's important to know which classical building blocks can be upgraded to quantum building blocks. So now I'm going to tell you about some classical building blocks, and we're going to go over whether you can upgrade them to quantum building blocks. So when I say upgrade, I don't mean just use the classical building block as is in a quantum algorithm. I mean, can you get a speed up over that building block in your quantum algorithm? That's what I mean. So let's start with the really easy one. We've been talking about this essentially for the entire tutorial, but let's just do it once again. You have query access to a list of numbers, and you want to decide if a particular number appears on that list. So how many queries, or how many uses of this oracle do you need? Classically, essentially, you need n. You just really have to look at every single number to decide if the particular number that you're looking for appears in this list. So that's the trivial upper bound, and this one you can speed up. This is Grover's algorithm, right? So we've talked about this quite a bit. I expressed Grover's algorithm slightly differently. I said that you have a string and it's either all zeros or one of the bits is not zero. That's the same as saying you're trying to decide if a list of numbers has your favorite number in it or not. Because what you can do is you can go to the list, and every time a number is not the number that you're looking for, you call it a zero. And if it is the number you're looking for, you call it a one. And now you're just looking at a list and you're saying, is it the all zeros string, or is it not the all zero string? So this is something you can solve with Grover's algorithm. You can do this quadratically faster, and that's tight. Okay, so this is just setting the stage. These are the kinds of questions that I want to talk about. Primitives and whether or not you can speed them up on a quantum computer. So this primitive, it's often called unstructured search because you're searching through something and there's no structure, so you don't know anything about the list. Okay, so let's make this a little more complicated. Here's a fun variant of this problem. Instead of you have a list of numbers, and instead of trying to find any occurrence of the number that you're looking for, let's say you're trying to find the first occurrence of this number. So first meaning from left to right. So how would you do this classically? You would just start looking left to right. Like you look at the first number, look at the second number, look at the third number, and so on. Let's say the number appears at position number r. Then after looking at r numbers, you found it, right? Like so, because it appears at position r, you've made r queries and you found the number. So this algorithm could be better than Grover's algorithm, right? So you could apply Grover, but that would be root n. But what if r is really small? Like what if the number you're looking for is really close to the left-hand side? You know, it's like maybe it's the first number. So maybe this is faster than Grover's algorithm. So the question is, can you do an algorithm that does the best of both worlds? As in, essentially, can you get a quadratic quantum speedup over the classical algorithm? Like let's say you're looking for the first occurrence, it's at position r. Can you do this quantumly with root r queries? So that would be a proper quantum quadratic speedup over this classical algorithm. Just a fun variation. It comes up in some algorithms. Maybe let's do an audience poll. What do people think? Can you quadratically speed this up on a quantum computer? Can you get a root R algorithm? How many people think yes, you can get a quadratic speed up? Good. Yes. Okay. Some people said yes. And what about no? Roughly the same number of people said no. Okay, good. Good. The audience poll is 50-50 on this one. And actually you can, which is nice. You can get a quadratic speed up. I'm pretty sure this was known before this paper, but I couldn't find an earlier citation. So this is the earliest paper I can find that explains how this algorithm works. It repeatedly uses Grover's algorithm. That's the key idea. But you have to take some care to make sure that you actually get root r, and you don't get any extra log factors. Oh, there's a question. Yeah. Oh, what's the problem? Okay, so again, you have query access to a list of n numbers. So query access was this thing we talked about earlier, this oracle and so on. And there's some specific number you're looking for, like some number you're given, and and you want to find it as fast as possible. And it appears at position r, but you don't know what r is, right? Because otherwise you'll just go look up r. And you want an algorithm that's faster when r is closer to the left-hand side. So like the classical algorithm has this nice property, right? If the number you're looking for is at first position, you'll just make one query. You won't make n queries. And so you want a quantum algorithm has the same property that if the number appears close to the left, it's square root of that number. Of course, in the worst case, it might appear all the way to the right. Then you would take root n, just like in Grover's algorithm. So you can achieve this. The position, yeah. So let's say in this case, r is the output. Yeah. Cool. Yeah. So that's a simple primitive. You might find it useful. Simple generalization of Grover's algorithm. Okay, let's do something different. It's not very different. It's again a search type problem, and this one is minimum finding. Also a primitive that comes up all over the place classically. So again, you have a query access to a list of n numbers, just like in Grover's algorithm. But now instead of now it's not just 0, 1 numbers like it was in Grover's algorithm. Now it's numbers over some, whatever. Maybe they're from 1 to n or something. And you want to find the smallest number. So again, classically, it takes n time. In fact, this is even harder than previously, because previously we were saying like you had a list of length n, and either all the bits were 0 or one of them was 1. And you had to find this. Now it's even harder than that. You're trying to find a minimum, right? So, how do you see that the previous problem's harder? Previous problem's easier. Like instead of zeros and ones, if we had like ones and zeros. So I gave you a string that was all ones, and either it was all ones or one of the bits was 0. Then finding out where the 0 is, that would be minimum finding, because 0 is smaller than 1. So this problem is harder than unstructured search, the problem we talked about earlier. So classically, it needs n. You really have to look at the whole list. Can you do this faster quantumly? Can you do this? And what would be the natural guess? The natural guess would be that you get a quadratic speedup. Can you do this in root n queries quantumly? So can you get the Grover speedup, but for the minimum finding problem? Okay, yeah, let's do audience poll. Who thinks yes, you can get a quadratic speedup? Okay, good. And who thinks no, there's no quadratic speedup for this problem? Okay, very few hands up. Okay, and the answer is yes. Yes, you can get a quadratic speedup. This is actually a very old quantum algorithm. It's from 1996. It's almost 28 years ago. Yeah, people have been doing quantum algorithms for a long time. All right, yeah, so you can do minimum finding faster. And so the reason I'm talking about these classical primitives that you can quantize is that, as I said before, like you have an algorithm in mind and you just do something like, you're like, oh, let me at this point find the minimum. So it would be nice if when you did this, you're like, oh, wait a second, there was a quantum speedup for minimum finding, and you go plug in the quantum speedup and you get a quantum speedup. So it's useful to know not just know what the primitives are, but also know when you can take an existing primitive and upgrade it to the quantum world. So that's kind of why I'm going over these classical primitives, and I'm asking whether or not you can upgrade it quantumly. Can you get speedups? So okay, let's do another fun one. Okay, ordered search. So this is where you're given a sorted list of numbers. So now what's different from the previous one, unstructured search, is that now your list is sorted. So you have some numbers, again, over some, maybe the numbers from 1 to n or something. And they're in increasing order. And you want to decide if a particular number appears in this list. So those of you who remember your classical algorithms will remember that classically you can do this with only log n queries. This is the binary search algorithm. What happens essentially is you just look at the middle of this list and you decide if, because it's sorted, your number has to appear either to the left of this or to the right of this if you look at the middle number. And so now you've cut your problem size in half, and then you keep recursing on this idea. After log n such queries, you'll find out whether your number exists on the list or not. Right, so now the question is, can you do binary search, or can you solve this ordered search problem faster on a quantum computer? Yeah, let's do an audience poll. This is a fun one. So who thinks there's a quantum speedup for this problem? Whoa, nobody. Or no one? Okay. And who thinks there? What did I ask? Yeah, who thinks there is a quantum? Yeah, who thinks there is no quantum speedup for binary search? Oh, everyone thinks there's no quantum speedup. Okay, interesting. Yeah. So actually, maybe everybody's right, because technically there is a quantum speedup, but it's a constant factor quantum speedup, so it's not very exciting. But there is a constant factor quantum speedup. It's a fun fact, not very useful, but if you're interested, these are some references. If you want to know how you can speed up binary search on a quantum computer, just a just a bit, not in a super useful way, but technically it's a speed. Okay, that was fun, but basically the answer is no. Yes, if you see binary search, you can't upgrade that to a quantum primitive and get any kind of speed up. Okay. Right. So, originally I gave this list of primitives and like there were some graph problems there. And I thought I would talk about some graph problems that you can speed up on a quantum computer. And then I realized there's just like a whole host of graph problems that you can speed up on a quantum computer. And these are just some examples. Decide if a graph is connected or it's bipartite or it's planar, contains a triangle. All of these have quantum speedups. And you could easily do like a 3-hour tutorial just on graph problems and quantum speedups. But I figured instead of doing that, I'll just give you some references. Here are some papers that do quantum, speedups for graph problems. The takeaway is if you're designing a quantum algorithm, and at the end you decide you realize that you're solving some kind of primitive about graphs, like you're trying to decide if a graph is connected, or you're trying to decide if a graph contains a particular clique as a subgraph, whatever. There might be a quantum speedup for that problem. You should look at some of these papers. There's like tons of papers on quantum algorithms for graph problems. So anyway, I'm not going to mention any of them in particular, but just lots of speedups are available. Sorry? Oh, good question. Are they all quadratic? So these ones are all quadratic, indeed, or even less than quadratic. Connectedness is like goes from like n squared to n to the 3 halves or something, and bipartiteness, some of these go like this. Triangle is a very interesting one. We still don't know the quantum complexity of this problem. It is an area of active research, and like there have been many papers that improve the best complexity of the triangle finding problem classically, quantumly, and we still don't know the correct answer. Whereas classically, the answer is well understood. Yeah, so most of these are quadratic, at least the ones listed on this slide. But that's I think that's just because of the techniques we use. It is possible to have super quadratic speedups, I think. I would have to think about it. Okay, so that was some graph problems. Let's move on to something. Okay, let's move on to some success probability amplification. So this is a thing that comes up in algorithms all the time, whether you're doing classical algorithms or quantum algorithms. You have an algorithm, and it solves the problem that you're trying to solve with some decent probability, 2/3. So I've been calling 2/3 probability high probability throughout this talk. But maybe you're not satisfied with 2/3. You're like 2/3 is, what is that? That's just like barely better than chance, right? Let's say I'm trying to compute a Boolean function. So the output is either 0 or 1. And you tell me that you have some algorithm and it computes it with slightly better than 50-50 probability. You can always solve the problem with 50-50 probability. You just answer a random bit and you'll be correct with 50% probability. And you come up with an algorithm that has 2/3 probability. Is that really a big deal? Like you might be like, come on, that's hardly better than chance. But in fact, what you can do is if you have an algorithm that succeeds with probability 2/3, you can always boost the success probability to a number arbitrarily close to 1. So you can make it 99%, or you can make it 0.999999 with like 100 nines, or you can make it 1 minus delta for some delta that's some decaying function of n, maybe. Delta could be like 1 over n, or it could be 1 over 2 to the n, and so on. So as long as you have some advantage over half, like 2/3, for example, you can always boost the success probability. This is why both in classical algorithms and quantum algorithms, you'll often just read the problem stated as compute this Boolean function with probability at least 2/3, because it doesn't matter if it's the constant is 2/3 or 3/4 or 4/5 or 0.99 or whatever. There is a way to increase the success probability. And that general idea is called success probability amplification. Sometimes it's called error reduction. And let me give you, I'll give you like 2 or 3 examples of how this works. Super useful. So yeah, so just to be super clear, you have this algorithm. When the answer is 0, it outputs 0 with probability at least 2/3. When it's 1, it outputs 1 with probability at least 2/3. And now you want to get an algorithm that you want to be even more sure of what the correct answer is. So we can think of this in terms of algorithms, but maybe there's an even simpler way to think about this, which is just I give you a coin. This coin is modeling the output of the algorithm. And the coin has 2 sides, heads or tails. So let's just call the 2 sides 0, 0, and 1. And when I flip it, the coin is biased towards the correct answer. So if the answer to my computational problem is actually 0, then the coin comes up 0 with probability at least 2/3. If it's 1, it comes up 1 with probability at least 2/3. And the question is, how would you get more confidence about the bias of your coin. Like, is your coin biased towards a 0 or biased towards a 1? If you just think about this, like I really physically hand you a coin and it's really biased towards heads or tails, what would you do to become more confident? You just toss the coin a bunch of times. So kind of the obvious thing to do. So the only question is how many times you have to toss it before you become 1 minus delta confident that it's really a hedge biased coin or a tails biased coin. And if you've seen this before, you know the answer. If you haven't, it's probably not something you can just work out off the top of your head. So let me tell you the answer. It's that you can run the algorithm log 1 over delta times. And then what do? You take the majority vote of your answers. So with the coin example, you toss your coin log 1 or delta times. And if you see more heads than tails, then you say it's a heads. You say it's a heads biased coin. If you see more tails than heads, then you say it's a tails biased coin. It's kind of the obvious thing to do, right? Like how else would you decide if which way a coin is biased? Just toss it a bunch of times and declare that the majority vote of the outcomes is the correct answer. So you can do this with algorithms. You can do this with classical algorithms. You have an algorithm, classical algorithm, has success probability 2/3. Run the algorithm this number of times, k number of times, and then you'll get k different outputs, right, from your k different runs of the classical algorithm. Take the majority vote. And this will now you'll have more confidence in the answer. And you have to take k to be this number if you want to have confidence 1 minus delta. Right, so this is a very basic primitive, comes up all the time in randomized algorithms. And now the question is, can you do better on a quantum computer, right? I think people knew that was what the question was going to be, because that's kind of the theme of all of these questions. Is there a quantum speedup for this? Can you do this success probability amplification better on a quantum computer? So if your underlying algorithm, if you're now allowed to use quantum algorithms, so you're not restricted to the strategy of just run the algorithm many times, but you can do something quantum, like you can run the algorithm, do Grover search on it, do whatever your favorite quantum algorithm is on. Can you do it better? Right, let's do audience poll. Who thinks you can do better with the quantum algorithm? Who thinks there's a quantum speed up? Yeah, there's somebody whose hand just went up way up. Right, good. Love quantum algorithms. Okay, good. A lot of people are saying yes. Okay, how about no? There's no quantum speed up. You still have to just the classical algorithm is the best algorithm that you can do. Oh, there's only 4 classical algorithms fans in the audience. Oh, that's a shame. Okay, so yeah, it's a good question. The audience is not divided on this, and in fact thinks there is a quantum speedup, but actually it turns out no, there's no quantum speedup. Yeah, see some people celebrating. Yeah, all right. So no, this is optimal. In fact, it was shown in this paper from a very long time ago. And the reason I wanted to mention this primitive is that when you I have this whole this whole thesis of this talk is that understand the primitives. It'll make it easier for you to understand quantum algorithms. If you see a quantum algorithm and its complexity expression has a log 1 or delta at the end of it, now you know where it comes from. It comes from this trick. So you can just forget about the log 1 or delta, understand the rest of the algorithm. You just apply this trick on the top of that, and you'll get the complexity of the algorithm with the log 1 or delta term. So you can always solve a problem with success probability 2/3. And if you want to boost the 2/3 to 1 minus delta, you do this trick, and it'll increase the complexity of the algorithm by log 1 or delta because you're running the algorithm log 1 or delta times. So this is one way in which primitives help, right? Because you can just start ignoring log 1 or deltas when you see them in algorithms because you know how to recover it. Okay, so this was just for computing Boolean functions. So you have a function that's either 0 or 1. You have some algorithm that works. We can boost it in this way. That's a question. Yeah, let's take the question.
Hi, just a quick one. Is it so here you've got like the success probability is 2/3, but does it work for like any success probability above like a half or something? Like do all the same results hold?
Yes, very good question. And in fact, that's going to be one of my next slides. But if it's any fixed number above 1/2, like 0.51 or something, this still works. But if it's arbitrarily close to a half, then this doesn't work, and I'll get to that.
Okay, great, thanks.
Yeah. Cool. Yeah. There's some interest in success probability amplification. Oh, another question. Let's take that. Why not? If the success, oh, you mean like when the algorithm succeeds, it flags that it has succeeded? It's not just, very good question, very good question. So it's like, if you have an algorithm, sometimes people call these heralded algorithms or something. But anyway, the algorithm tells you whether it's got the right answer. I have a slide about that, so just wait 3 slides. Okay, good. Let's, right. So this was just for a Boolean function, right? You have an algorithm. It either says, the only 2 possible answers is yes or no. And if you have 2/3 success probability, you can make it arbitrarily close to 1. This is great. So from now on, you can only think about 2/3 success probability algorithms, but for Boolean functions where the output is 0 or 1. But not every problem you care about has a Boolean output, right? So let's talk about another common scenario, which is your output is a real number. This also happens, like you're trying to compute some expectation value of an observable, you're trying to compute some, I don't know, I don't need to give you examples of real numbers, like these come up all over the place, right? The whole world is not Boolean. So now you have an algorithm that outputs some number, and the number is promised to be epsilon close to the correct answer. So, right? Epsilon close just in the usual sense of what it means to be epsilon close for two real numbers, which means if you subtract them and take the absolute value that's less than epsilon. So you have a quantum or classical algorithm, doesn't matter, which is supposed to compute some real number for you. Maybe it's an expectation value or something. And its guarantee is that it always, not always, with probability at least 2/3 gives you a number that's close enough. So let's say epsilon was the threshold that you were satisfied. You were satisfied with an answer that was epsilon close. Now your algorithm is giving you a number that's at least 2/3, it's giving you an answer that's at least epsilon close, and it's doing it most of the time, like with probability at least 2/3. Can you boost this to 1 minus delta? So one thing to notice is the previous algorithm doesn't really make too much sense. Like if you just run the algorithm anytime, you might just get, say you run it k times, you might just get k different real numbers as output. And like, what does it mean to take the majority vote? Like there's not even like, for bits, there are only two possible options, 0 or 1, you just take the majority. But for real numbers, that doesn't really make sense, right? So what do you do? So, okay, so I'll tell you what, like the algorithm is of course to run this previous algorithm k times, but the question is, what do you do with the k real number outputs? So you want to become more confident in your answer. You want to do something with these k real number outputs, right? Okay, so what could you do? One kind of straightforward thing you could do is you can take the average of these numbers, right? Maybe some of you were thinking of that. There's k numbers, take the mean. Another thing you can do is take the median. Third thing you can do is take the mode, right? The mean, median, and mode. These are three fundamental statistics we learn about in statistics class. So what is the correct answer? Let's do audience poll, right? Let's start with mean. How many people think you should take the mean of these numbers to get a good estimate of the final answer? No love for the mean? Okay. Median. How many people think median is the correct answer? Oh, lots of love for the median. Oh, awesome. What about the mode, which is the most commonly occurring answer? Okay. One person, very little love for the mode. Okay, so the answer is indeed the median. Those of you who said median, yeah, give yourselves a round of applause. The median works. It's actually not very hard to prove. You can actually use the proof of the Boolean case to prove this median thing. But here's the second question. Can you get a quantum speedup for this? Right? So this algorithm also works quantumly, of course. You take your quantum algorithm that's outputting some real number, run it log 1 or delta times, take the median of the outputs, just a totally classical strategy. Can you get a quantum speedup? Okay, who thinks there's a quantum speedup? A few people think there's a quantum speedup. How many people think there's no quantum speedup? Slightly more people think there's no quantum speedup. Okay, so the correct answer is no, because this is even harder than the previous example we just did, right? Because this is a real number. Like previously, we were just doing 0, 1 valued functions. Okay, so the reason I'm mentioning success probability amplification is that this idea is rediscovered like over and over again, because it's such a nice idea, right? Like you want to compute some real number with higher, want to get more success probability, more confidence. Just do it over and over again. Take the median of the answers. So you'll see this all over the place. One place that I've seen it a bunch of times is for phase estimation protocols. So I don't know why people keep rediscovering this for phase estimation, but you can do this for phase estimation. So I'll talk about phase estimation a little later, but like that's a primitive where you do have to output a real number. You're trying to output some eigenvalue or something, and you want to be close to it, and then you want to have high confidence. The high confidence part, you can always make it log 1 or delta. You don't have to suffer worse complexities because of this trick. Okay, good. So this was just very similar to the previous slide, but now let's do something slightly different. This answers a question that I just got, which is, what if you're not trying to boost from 2/3 to arbitrarily close to 1, but you have an algorithm that's slightly better than chance. So as I said, an algorithm whose success probability is just 50-50 for a Boolean function is completely useless, right? Because I can give you an algorithm that has 50-50 chance of computing the Boolean function correctly, which is just toss a coin. That's the output. But this is not that. This is slightly better than half. It's half plus epsilon. So epsilon can be really small. Epsilon might be 0.001, but epsilon might be also like 1 over n or 1 over 2 to the n or something. Epsilon could be a function of the input size. So you have an algorithm that performs slightly better than chance, and now you want to make this 2/3. And why do we just want to make this 2/3? Because as we discussed, once you have 2/3, you can go arbitrarily close to 1. So it doesn't matter. We just want to go to 2/3. So what do you do? So let's first start classically. What do you do? Again, like in all of these success probability amplification questions, the algorithm is always going to be run the algorithm many times and take the majority vote. So it's a Boolean function. You can just take the majority vote. So same thing. Think of it as a coin. I give you a coin. It has a slight bias towards heads or tails. So let's just think of it as like maybe it's 51% bias towards heads or tails. And you want to become very confident about this. What do? Just toss the coin a lot of times, right? Maybe toss it like, I don't know, 1,000 times. It seems like that should be reasonable, right? Because if you have like 51% bias towards heads, let's say, if you toss it 1,000 times, you might think that you'll get like, I don't know, 510 heads or something. That's not how probabilities work, but that's you might think that's kind of how you get it. So the number of times you have to toss it will, of course, be a function of epsilon. The smaller that epsilon is, the closer it is to basically being useless, the more you'll have to toss the coin. So clearly, the number of times you have to toss this coin is going to be a function of epsilon, but it's going to be a decreasing function of epsilon, as in it's going to be a function of 1 over epsilon. Sorry. So as epsilon gets smaller, you have to toss the coin more. So the question is, what function of epsilon is it? Just for classical algorithms. And I'll tell you what the 3 options are. It's let's say log 1 over epsilon, just like previously. It's 1 over epsilon or 1 over epsilon squared. These are our 3 options. So let's do an audience poll. Who thinks log 1 over epsilon? Very few takers for log 1 over epsilon. What about 1 over epsilon? A few more takers for 1 over epsilon? Okay, what about 1 over epsilon squared? Okay, many. Okay, I was afraid that people stopped caring about audience polls, and I was a bit sad. But okay, a lot of people raised their hands for 1 over epsilon squared, so good. People still care. People just didn't care for the first 2 options, and that is actually correct. 1 over epsilon squared is the correct answer. It's a super fun thing to think about. So if you've never seen this before, it's a totally classical question about statistics and coins. Give you a coin with bias half plus epsilon. How many times do you have to toss it so that you'll become pretty confident of which way it's biased? I'm promising you that's either biased towards heads or tails with probability half plus epsilon. Yeah, think about this. Super fun question. But everyone knows what the next question is going to be. Is there a quantum speedup for this question? So yeah, let's just do yes or no. Is there a quantum speedup for this? Let's start with yes. Who thinks there's a quantum speedup? Yeah, lots of quantum algorithms fans. Right, yeah, quantum algorithms are the best. Okay, who thinks there's no quantum speedup? Okay, a pretty sizable fraction of the audience thinks there's no quantum speedup. And yes, it turns out there is a quantum speedup. In fact, you can do this with 1 over epsilon quantumly. So the notion of uses of the algorithm is a little subtle here. So this is why I talked about these input models and so on before. So here by uses of the algorithm, I mean is if you're giving me an algorithm, whether it's classical or quantum, I can express it as a unitary, of course. And now what I mean by unitary is I'm going to use your circuit U and its inverse 1 over epsilon times. And this algorithm that uses it this number of times and solves the problem is called amplitude amplification, and is also a very old primitive, very useful primitive, and gives you a quadratic speedup over this. Good. So this is the question that we got earlier from somewhere here, that if it's just slightly better than half, how do I make it 2/3? You can do it both classically and quantumly, but quantumly you can do it better. So if you see a classical algorithm that's doing this strategy, now you know you can always boost it to a quantum algorithm and you'll get a quadratic speedup. So that's great. And finally, finally, let's get to this question that was asked somewhere over there, which is, what if you have an algorithm that tells you when it gets the correct answer? So this is kind of weird, but it's not super weird because we got a question about it even before I talked about it, which is, so you have an algorithm, it runs for some amount of time, and then it stops, and then it either says, I don't know the answer, in which case it doesn't know the answer, or it gives you an answer, but when it gives you the answer, it's always correct. So this is the property of the algorithm. Okay, so it's kind of weird, but does the setup make sense, right? So you have an algorithm, it ends by saying, I don't know, or I know the answer and this is the answer. These are the only 2 options. It never gives you the wrong answer. That's important to know. It says, I don't know, or it tells you the correct answer. Now, the thing is that it mostly just answers, I don't know. So most of the time, the algorithm doesn't know, but once in a while, with probability epsilon, which is a tiny number, it says the answer, which is great, but now you would like an algorithm that actually succeeds a reasonable number of times. It's like you would actually like to know what the answer is. So you would like to boost this epsilon to, let's say, a constant, a half, or 0.99. Doesn't really matter. The question is, let's talk about classical algorithms first. How many times do you have to repeat this algorithm? We can also think about this in terms of coins. Let me reformulate it in terms of coins. You might have more intuition about this again. You have a coin where heads corresponds to getting the correct answer and tails corresponds to the algorithm saying, I don't know. The heads probability is epsilon. And the question is, how many times do you have to toss this coin so I see heads at least once? Because if you see the heads, then you know the answer. Right? So classical question, classical coin, epsilon probability of heads. How many times do you have to toss it so you see a heads at least once? Um, right, I should give you some choices. Right, so let's do choices 1 over epsilon, log 1 over epsilon, and 1 over epsilon squared. Same choices that we had last time, because that seems reasonable. Obviously, it should go like some function of 1 over epsilon. As epsilon gets smaller, the problem gets harder, so it should be a function of 1 over epsilon. Okay, so that's clear. So let's start with log 1 over epsilon. How many people think you have to toss this coin log 1 over epsilon times? Cool, some love for log 1 over epsilon. How many people think it's 1 over epsilon? Oh, many people think it's 1 over epsilon. Wow, good, overwhelming support for 1 over epsilon. What about 1 over epsilon squared? Oh, very little support. We saw that function just on the previous slide. Come on, no love for this function? Okay. All right, all right. Okay, it is 1 over epsilon. And this is, yeah, somewhat reasonable, right? Like if you have heads probability P, you have to kind of toss a coin like 1 over P times before it comes heads. If you haven't seen this before, yeah, think about it. It's fun to work out. Okay, so that was classical. But now the important question, what happens quantumly, right? We have a quantum algorithm, same property, this weird property that it either succeeds, either gives the correct answer or it says, I don't know, epsilon probability. Can you do better quantumly? So I'll just ask the yes or no question. Is there a quantum speedup? So how many people say yes, there's a quantum speedup? Okay, a few people. Okay, how many people think no quantum speedup? Even fewer people. Okay, so I guess people don't have any intuition about this question, is what I'm taking away. And the answer is yes, there is a quantum speedup. You get a full quadratic speedup, again using amplitude amplification, actually. And it's a speedup in the same sense. You have to use the algorithm, the unitary, and its inverse, but you get a quadratic speedup. So yeah, whoever asked that question earlier about what if you have a quantum algorithm or classical algorithm that for some reason has this unusual property, there is a quantum speedup for this primitive. Pretty cool. Okay, so I think that is the end of my success probability amplification sequence. How am I doing on time? Okay, good. Let me tell you one last primitive, which is just kind of fun, which is I'll give you query access to a function, and it has a domain of size n and a codomain of size m, which is bigger than n. And you have to decide if the function is 1-to-1 or 2-to-1. So what does that mean? A function is 1-to-1 if every input gets mapped to a different output, and it's 2-to-1 if, like, every output symbol that's mapped to has two preimages. Right? So I'm telling you the function has one of these two properties. It's either 1-to-1 or 2-to-1. How many times do you have to access this function to decide which one of these two properties holds? And I'm saying classically, with a deterministic algorithm, there's really nothing you can do. You really have to evaluate the function at pretty much everywhere in the domain. Because, and why is that? The argument is easy to see as well. You value the function on 1, maybe the function outputs 1. You say, what is f of 2? You get 2. What is f of 3? You get 3. F of 4. And this goes on all the way till n over 2. You evaluate f of n over 2, it tells you n over 2. Now you still don't know if it's a 1-to-1 or 2-to-1 function, right? Because if the function continued this way, that would be a 1-to-1 function. Or it could now start mapping back, like f of n over 2 plus 1 could be 1 again, and f of n over 2 plus 2 could be 2, and then it would be a 2-to-1 function. So until you've evaluated the function at n over 2 positions, you don't know the answer. So this is the classical deterministic optimal strategy. So here, I want to make a distinction between classical deterministic algorithms and randomized algorithms. So who thinks you can do better with randomized algorithms? This question. Lots of people think yes. Who thinks there's no speed up for a randomized algorithm? Nobody thinks that. Okay, very little love for that. And yes, actually there is a randomized speedup, and it's square root of n. And this is due to the birthday paradox. If you haven't heard of the birthday paradox, super cool. Look it up on Wikipedia. It's this thing where if you take 23 people in a room, it's pretty likely that 2 of them share the same birthday, which is a paradox because there's 365 different birthdays. So you're like, wait, what's going on? But it's actually the same reason why this happens. So yeah, super fun. So even classically between deterministic and randomized algorithms, there's a quadratic speedup. So now we go to quantum algorithms. Question is there a further speedup for quantum algorithms? Or is the best that quantum algorithms do just the same as the randomized complexity? So who thinks there's a quantum speedup? Oh, wow, okay. Lots of love for quantum algorithms. Who thinks there's no quantum speedup? Oh, very little support for no quantum speedup. Okay, good. Yes, there is a quantum speedup. You can actually do this as n to the 1/3. So I don't know what people were thinking, but like n, root n, and the next option is probably n to the 1/3, right? Like that kind of makes sense. You can, it's called the collision algorithm. It was shown in this paper from 1997, and in fact, it's optimal. You can't do better than n to the 1/3, and that was shown in these two papers over here. Okay, cool. So that brings me to the end of the classical primitives that you can make quantum part of this talk. And now let me talk about some primitives that are natively quantum. So they're not upgrades of classical primitives. They're just primitives that it kind of just makes sense to think of them as just quantum primitives. Like yeah, I'm not going to do this thing of like this is the classical algorithm and can we upgrade to quantum? There's none of that. I'll just tell you what the quantum primitive is because the classical analog just doesn't really make so much sense. But this is a good place to stop for questions. I see there's a question over there. Let me stop. What's the intuition for the speed up for what? Oh, the collision problem. Yeah, you'll have to read the paper now, won't you? It's the short version is that it uses Grover's algorithm. That's part of it, but that in itself is not sufficient. It yeah, I'll say read the paper. It's a fun one. Actually, another interesting fact: that algorithm needs CQ-RAM. Going back to this discussion we're having with CQ-RAM and QQ-RAM, that one needs CQ-RAM. So yeah, look at the original paper. It's very easy to understand. It's not a complicated algorithm, but it's very nice. Any other questions? Yeah, because I'm kind of shifting gears a little bit. Now I'll talk about genuinely quantum primitives that are not quantizations of classical primitives. Okay, good. Okay, so let's talk about quantum primitives. And oh, one question before we add it. Sorry, so you said for Simon's problem? Sorry. Oh, this problem. Oh, this is not Simon's problem. This is just deciding if a function is 1 to 1 or 2 to 1. Simon's problem has much more structure. So you have to decide more stuff. Yeah. So this is a different problem. All right, let's take one last question and move. Well, I don't know. I mean, if you just want to get this result that you need to enter the 1/3 queries, you're just counting the number of uses of this oracle, then you don't need to talk about QRAM and so on. I just mean if you want to instantiate this as a circuit at the end of the day, so like this function f is given to you as a circuit, like maybe it's a hash function or something, and you're trying to decide if the hash function has collisions. To finally execute the entire algorithm truly in the circuit model, then you would need CQRAM. So to just get this result, this question is not really about circuit complexity, it's just about how many times you use an oracle. So I just mean if you end up wanting to use this algorithm to do some cryptographic tasks with hash functions, you will generally need CQRAM, as far as I know. Maybe there are some versions of this algorithm that don't need it, but then they don't get the same complexity. Okay, maybe let's move on to genuinely quantum primitives, or natively quantum primitives. And some of these have names, like phase estimation and so on. And some of these don't have names. And I wanted to say, like, think of the little ones that don't have names as well and give them some love. And next time when you're reading quantum algorithms papers, try to add these to your toolbox. And I'll just give you one example because it's very hard to find stuff that doesn't have a name. But this is an example of a primitive that doesn't have a name, which I really like. And it's about reflecting about a quantum state. So the question is the following. You want to create the unitary map, R psi, which is identity minus 2 psi psi. What this does is it takes ket psi, maps it to minus ket psi, and it takes everything orthogonal to ket psi and maps it to itself. So it's a reflection about the state ket psi. And the question is, can you do this given a circuit that prepares ket psi? And the answer is yes, you can. And it's actually not hard to do. If you have a circuit U that prepares ket psi starting from all zeros, then this product of 3 unitaries over here, the preparation circuit U, a reflection about the all zero state, and U inverse will indeed do R psi. So if you can create a state, you can reflect about a state. That's the takeaway here. This is a simple, nice, cute primitive. Doesn't have a name. Maybe we should give it a name. But recall, I was talking about earlier, like what kind of access models could you have to a quantum state? One of them was you have access to a circuit that prepares state. But what if instead of having a circuit that prepares a state, you just have copies of the state? So I give you as input a bunch of copies of ket psi. The question is, can you now create an operator that's a reflection about ket psi? Okay, yeah, let's make this an audience poll. So okay, there's one trivial way in which you can do this is you take enough copies of KetSci that you can do full quantum state tomography on KetSci and write down a classical description of KetSci, and then you can create a unitary that does. Okay, so that's not what I mean. I mean, is there a strategy that uses some number of copies of KetSci that is independent of the dimension of KetSci? So yeah, if you it's okay if it's approximate, you can depend on the approximation parameter, but you shouldn't depend on the dimension. So is there a way to create a reflection about psi using only copies of psi, not the unitary that creates psi? This is maybe a good audience question. So who thinks there is a way? Yes, there's a way to do this. A few hands up. Okay, and who thinks there's no way to do this, just given copies of psi? Okay, yeah, this was maybe a question that people don't have too much intuition about. But actually, yes, you can. You can do this, and you can implement a map that's epsilon close in diamond norm to R psi using only 1 over epsilon copies of psi. Pretty fun primitive, not very well known, so also doesn't have a name. And you can see the algorithm is explained in any one of these papers. And yeah, it kind of shows you also the difference in power between these two models, right? Having the circuit makes life real easy. You can exactly do the reflection with just 2 uses of the circuit. Whereas if you have copies, it's like it degrades with the error, and so like you need to make more copies. You need more copies to get better and better in error. So these two models really are different: copies of psi versus a unitary that prepares psi. Okay, so this is just one example of a simple primitive. I don't have other examples of primitives that don't have names. As I said, it's hard to find such things. So let me tell you about some popular quantum primitives that do have names and are famous. So one is amplitude amplification. We saw a few examples already. Amplitude amplification is just like used all over the place. It's a generalization of Grover's algorithm, but very widely applicable. It has its own generalizations further called variable time amplitude amplification, oblivious amplitude amplification, Monte Carlo mean estimation, etc. So that's a good primitive to know. Quantum phase estimation. This is used all over the place. Used in Shor's algorithm. Used in many algorithms for that I'll talk about in a while. Hamiltonian simulation itself is both a primitive and also a problem that you want to solve in some sense. Like you want to simulate the time dynamics of quantum systems on quantum computers. That is, in fact, the original application of quantum computers that Richard Feynman proposed in the 80s. But you can also use this as a primitive to solve other problems, other linear algebraic tasks that have nothing to do with Schrodinger's equation or simulating quantum systems on a quantum computer. So I like to think of it as a very useful primitive as well. The quantum Fourier transform or Hadamard transform or Fourier sampling, this is at the heart of many quantum algorithms that you might know and love. The quantum Fourier transform is used in Shor's algorithm. The Hadamard transform is used in like the Bernstein-Vazirani algorithm, Simon's algorithm, the Deutsch-Jozsa algorithm, the four relation problem, if you've heard of this. Okay, then there's the quantum adiabatic algorithm and QAOA, which is kind of like a discretization of the quantum adiabatic algorithm, also an old algorithmic idea in quantum algorithms. This one is sometimes harder to analyze the runtime of, so maybe you haven't seen it as much as the other ones. I don't know, depends on what circle you hang out in. But if you're talking about like proving rigorous bounds on how much time it takes, it's sometimes hard to do this with the adiabatic algorithm. And then there's this family of like, I'd say, new quantum algorithm primitives from the last 10 years or so, 10 years. I think that's right. Yeah, I think LCU is from 2014 or 2015. And yeah, block encodings are used in that. And these are, yeah, new fancy quantum algorithmic primitives that give you speed ups for many problems. And I will talk about some of these in the remaining time that I have. Cool. So let me tell you what am I? Okay, I'll tell you amplitude amplification. This one's really easy to explain. Oh, there's a question. Let me take the question first. So I put HHL in the first list, so I didn't want to put it in this list again. But you could certainly think of it as an algorithmic primitive. That's totally fine. And in fact, I will spend some time explaining HHL. So maybe, yeah, maybe HHL should be on this list. It's arguable. This whole distinction that I was making is kind of arbitrary anyway. It's just some way for me to divide it into two parts and make it manageable to digest. Okay, let me tell you about amplitude amplification. Super useful primitive. Comes up all over the place. What's going on? You have some unitary U. You act on some initial state, let's say the all zero state, and you get a superposition of two states that are flagged by a qubit. The first qubit tells you whether it's the good state, the state you want, or the bad state, the state you don't want. The good state has amplitude root p. The question is, can you now create this good state for me? That's the computational task. There's one simple way to do this, which is start with the state over here and just measure the first qubit. If you get 0, then you know for sure that the second register is the good state, right? So you can just do this over and over again. And what's the probability that you get a 0? It's this number squared, amplitude squared, so it's probability p. And we already talked about this before, right? If you have an algorithm with success probability p, and you want to get constant success probability, you have to do this 1 over p times. That's the classical strategy. And in fact, that's the naive algorithm. Just keep measuring the first register of u 0 to the m. With probability 1 over p, you'll get the state you want. And amplitude amplification gives you a speed up over this. It does this with only root 1 over root p uses of this unitary and its inverse. So this might seem familiar because many of the things I was talking about earlier are powered by amplitude amplification. So same setup. Good. So this is one primitive. Let's talk about phase estimation, right? So I mentioned this primitive a couple of times. It is very useful. You can use it to solve, you can use it inside Shor's algorithm and such. You can use it for doing the HHL, the quantum linear systems algorithm. You can use it for many things. All right, so what are you given in phase estimation, right? So you're given three things. First, you're given a black box that implements a control unitary. Okay, cool. That's just some control unitary. The second thing you're given is an eigenstate of this unitary. So you're given one copy of the state, just one copy. And its promise is that it's an eigenstate, and its eigenvalue is something, I'm going to call it e to the ix. It's a unitary, so its eigenvalues are always complex numbers of unit modulus, so I can always think of it as e to the ix for some number x between 0 and 2 pi. And you're given an accuracy parameter epsilon. And what I want from you is an approximation to this value x, basically. I want you to output an angle x tilde, which is, again, a number between 0 and 2 pi, such that x tilde is epsilon close to x with high probability. Right? And everyone remembers why we only talk about probability 2/3, because if you want a better probability, just do it yourself. Do the success probability amplification part yourself. Cool. So phase estimation solves this problem. And the question is, how many times does it use control U? It only gets one copy of the state, so it can't use the state more number of times. So it can only use control U a bunch of times, and it uses it 1 over epsilon times. And yeah, remember from before, you can always make this 1 over epsilon times log 1 over delta if you want to make this 2/3 into 1 over delta. That's just the stuff we've been talking about. Okay, cool. That's phase estimation. But let me say a little more about what phase estimation actually does, or like what's the output state. So phase estimation actually performs the following map. It takes the state ket psi, some ancilla set to 0. It leaves ket psi as it is, doesn't do anything to it, doesn't destroy the state. But in the second register, it creates a superposition of various values of x tilde. This is the answer, this approximation to x, and some garbage state that could be entangled with this x tilde. And the guarantee is that, in this 1 minus delta version, let's say, that when you measure the second register, you'll get an x tilde that's epsilon close to x with probability 1 minus delta. So I'm just saying exactly what happens, just so it's clear that phase estimation doesn't even destroy the state you started out with. It just writes down in a second register some stuff that you can use in your algorithm. And yeah, what's nice is you can also undo this map and erase this stuff later on. So like, let's say you use this stuff in your algorithm to do something, and then later on you're like, I don't want this crap lying around. You just undo this phase estimation map and you get back this. So that's what phase estimation does when you're given an eigenstate of the unitary. But if you're given something that's a superposition of eigenstates, we can infer what the algorithm would do just by linearity. This is linear algebra. If I tell you what an operator does on all the eigenstates and the eigenstates span the space, then you know what the operator does on the entire space. Okay, so that's the phase estimation algorithm. Good. Everyone's happy with phase estimation? Right. It's a great algorithm, useful all over the place. And the third one I want to tell you about is Hamiltonian simulation. Also super useful primitive. As I said, you can also think of it as an application of quantum computers, but it's very nice as a primitive as well. But here I'm going to have to tell you what a Hamiltonian is. So there's like some part of this audience who's just like, of course I know what a Hamiltonian is. Like, who do you think I am? And there's a different part of this audience who's just like, what is a what? So this is all you need to know about Hamiltonians for this talk. A Hamiltonian on n qubits is a 2 to the n by 2 to the n Hermitian matrix. Okay, that's it. That's what a Hamiltonian is. And now I want to talk about two properties a Hamiltonian might have. It might be sparse. And what I mean by sparse is, although it's a 2 to the n by 2 to the n matrix, it only has polynomially many non-zero entries in any row or column. That's what I call a sparse matrix. This is a parenthetical remark for those people who know what a k-local Hamiltonian is. Like, for example, if you went to Anurag Anshu's tutorial yesterday, you would know what a k-local Hamiltonian is. So if you know what that is, then any k-local Hamiltonian with constant locality is also an example of a sparse Hamiltonian. So sparse Hamiltonians is more general than k-local Hamiltonians. If you don't know what a k-local Hamiltonian is, doesn't matter. And finally, I'll say a Hamiltonian is efficiently row computable if you can, not only is it sparse, but you can actually compute the locations and values of these sparse entries. So sparseness is just a mathematical property of a matrix, but row computability is an algorithmic notion. It means that not only is it sparse, but you can actually tell me where the sparse numbers are. Okay, good. This is all you need to know about Hamiltonians for this talk at least. And the Hamiltonian simulation problem is the following problem. I give you as input a row computable Hamiltonian H, a time t, and an error epsilon. And your task is to implement a quantum circuit which is epsilon close to this unitary, e to the minus iht. If you've never seen this before, you might be like, wait, why is this even a unitary? It is. If h is Hermitian, then e to the minus ih times any real number is a unitary. You can prove this. And if you haven't seen this before, you're like, wait, why would I care about this totally arbitrary function, e to the minus iht? The reason is this is the solution of the Schrodinger equation for time-independent Hamiltonians. So it comes up when you're doing, if you want to understand the time evolution of quantum systems. But anyway, we don't have to worry about that if you don't want to worry about the application. As a primitive, it's just a primitive. It just does this for you. And what's the complexity? The best known current algorithms have complexity that goes like some polynomial in n, times some function that's proportional to the largest entry in the Hamiltonian times the time plus some log 1 or epsilon. And the best algorithms currently are based on quantum signal processing or quantum singular value transformation, which was one of the primitives I talked about on my primitive slide. Okay, cool. So I talked about three primitives: Hamiltonian simulation, quantum phase estimation, and amplitude amplification. And I want to show you how we can do something interesting using only these primitives. Right? So my, the thesis of this talk has been that if you know the building blocks, you can do cool stuff, you can make new algorithms. So let me show you how to do something with just these primitives. And let's talk about the quantum linear systems problem. So this is this problem, sometimes it's called the HHL problem, named after the authors who originally proposed this problem. HHL is Harrow, Hasidim, and Lloyd. So what's going on this? This is some kind of quantum analog of solving a linear system of equations. So you're given some matrix, A, and it happens to be sparse and row computable. So remember those definitions from the previous slide. And additionally, you're told that the spectral norm of A is at most 1, and the spectral norm of A inverse is at most kappa. This implies that the condition number of the matrix is kappa, if you know what the condition number is. If you don't, that's fine. Just remember this. So you're given this matrix. Then you're given a quantum state B, but you're not just given a copy of this quantum state B, but in fact, you're given a quantum circuit that prepares the state B. These are different things. Right? So remember, we talked about different ways you could be given a quantum state, copies versus given the circuit. You're actually given the circuit that prepares B, and this is important. And you're given an accuracy parameter, epsilon. And what I want to do is create a quantum state that is epsilon close to this state over here. So A inverse times ket B is not necessarily a valid quantum state because it might not be normalized. So we divide by its norm to make it norm 1 because quantum states need to have norm 1. Okay, so now you might be thinking, wait, why is this even related to why is this related to linear systems? Why did I call this a linear systems problem? Because in the traditional linear systems problem, like that you might have seen before, you're given a matrix A and a vector B, and you need to solve the system of equations AX equals B. And the solution to that is just X is equal to A inverse times B. And so now if you look at the two things, like A inverse times B and A inverse times ket B correctly normalized, they look like kind of the same thing, right? So this is why it's called the quantum linear systems problem. It's not the same problem, it's just kind of like a quantum analog of that problem. Okay, so this is the quantum linear systems problem. And I'll show you how to solve this problem using, in fact, only two primitives, Hamiltonian simulation and phase estimation. So this algorithm uses just two primitives and solves this problem. And it's not very complicated. This is maybe the most technical part of this talk so far, because I'm going to actually step through an algorithm and what you can do and what you can't do, but hopefully it'll make sense. Okay, so step one. So it's a couple of steps to this algorithm, maybe 4. So the first step is I'm just going to assume A is Hermitian. So you're going to be like, wait, why can you assume A is Hermitian? Because the original problem doesn't say A is Hermitian. But this is essentially without loss of generality because of a simple trick, which I won't really explain in detail, but this is one of those primitives that doesn't really have a name. But it's like when you want to solve a linear algebraic task about arbitrary matrices, but you only know how to solve it about Hermitian matrices, then one trick you can do is define a new Hermitian matrix from your old non-Hermitian matrix in the following way. If your old non-Hermitian matrix is A, you can define a Hermitian matrix that's 0, A dagger 0. It's a block matrix, and this matrix will always be Hermitian. So it's just a fun linear algebra trick. It's a primitive. But anyway, so because of that, you can just assume A is Hermitian. So just forget about that if you didn't understand the trick. A is Hermitian. So therefore, A has some spectral decomposition. So I'm going to call its eigenvectors ket lambda j. I'm going to call its eigenvalues lambda j. So we're trying to implement this guy, right? A inverse times ket B. So let's express ket B in this eigenbasis of A, right? So that's a full set of eigenvectors. I can express any vector in terms of this as a linear combination of these eigenvectors, and I'm going to call the coefficients alpha j. So I have ket B, which is alpha j ket lambda j, sum over j, and I want to transform it to A inverse times ket B. And now because I've expressed ket B in the eigenbasis of A, I can just apply A inverse, and I know what happens. I get lambda j inverse. Okay? So I want to create the state that's a superposition over j's of alpha j lambda j inverse ket lambda j, but what I have is alpha j ket lambda j. So this is the task I'm trying to solve. Okay, we haven't really done anything. I'm just trying to simplify the task that we're trying to solve using better notation. So I'm just going to copy that on the next slide. So this is our goal. Create this state from this state. Okay, cool. So what can we do? So what would be really nice? What would be really nice is if we could just take a state ket lambda j and map it to ket lambda j inverse times lambda j. Sorry, lambda j inverse times ket lambda j in superposition. If you could just do this, you have this guy. Just replace every occurrence of this ket with lambda j inverse times the ket. If you could do that, it would be done. Right? That's what we want to do. But you can't do this. This is not even a unitary operation. Right? So this is just like, no, you can't do this. But this is the goal. Just this is the thing we're being motivated by. We want to go in the eigenbasis of the operator. We want to put 1 over the eigenvalue in front of the eigenstate. That's what the linear systems problem is fundamentally. The only annoying part is that's not a unitary map. You can't. This is not even meaningful. Okay, that's a small obstacle. It's not even unitary. But there's something else you can do that is unitary, which is this. You can take lambda j and keep lambda j around, and the second register create this qubit. So this is indeed a qubit. It's correctly normalized because I assumed earlier that lambda j inverses are all bounded by kappa. So this first number is at most 1. And the first number is 1, and this number is just whatever it needs to be for this to be a qubit, for the L2 norm to be 1. So this is a thing that makes sense to do, right? Because I'm just adding a qubit here. So let's try to do this instead. So we could easily just create this qubit if you told me what lambda j was. Like if you just told me what lambda j was on a piece of paper and you told me what kappa was, I can compute this ratio and I can just create this qubit with some conditional rotation of something or the other. But we don't know what the lambda j is. In fact, what's worse is there's not one lambda j. You want to do this in superposition inside a quantum algorithm. So it's not like I told you fix lambda j. You want to do this in all branches of the superposition correctly. So what would be really nice is if you had an algorithm that told you what lambda j was in superposition. So you have some superposition of lambda j's. This is the state you're starting out with. And what I want is an algorithm that writes down in a second register some approximation of lambda j for me. So this. It takes lambda j, ket lambda j, it keeps that state around, but in a second register, it writes down some kind of binary representation of, what is the approximate value of this this lambda j number. So this should remind you of the quantum phase estimation algorithm because that's what it does. It gives you something like this, except phase estimation needed something as input, right? It needed an operator whose eigenvalues were e to the I lambda j. And then what phase estimation would do is write down an approximation of lambda j in another register. So do we have an operator whose eigenvalues are e to the I lambda j? Yes, we do. It's e to the IA. And that's what the Hamiltonian simulation problem solves for you, because that's what, we talked about Hamiltonian simulation. We said that for a given matrix A, it can give you the operator e to the IA t for any t. Here t is 1, so it can give you e to the IA. So cool. So we have phase estimation, we have Hamiltonian simulation. So now we can write down this phase over here, and we can do this conditional rotation. And that's pretty cool. So then what we can do is create this superposition, this qubit in superposition. So we have this superposition over the eigenstates, lambda j. That part stays the same. And the second register, we can create this extra qubit in superposition using phase estimation, Hamiltonian simulation. Then you undo phase estimation, so all of that stuff is gone. And what's remaining is that you just measure this register, this ket 0 or ket 1. If you get ket 0, then you have the state you wanted, which is ket alpha j, ket lambda j inverse acting on ket lambda j here. There's a kappa in the denominator, and what that means is that the probability of this outcome is 1 over kappa squared. So what do we do when we have an algorithm whose probability of some good outcome is 1 over kappa squared? We just run it like order kappa squared time, and then it'll succeed at least once. And you can do that. So just do this 1 over the probability number of times, so just kappa squared times the cost of these two algorithms. I didn't tell you exactly what the cost is, but just take my word for it. It's some polynomial times kappa over epsilon. And this gives you a kappa cubed over epsilon algorithm for this linear systems problem. Cool, so that's an algorithm for solving this problem. Does anyone notice a classical primitive here that can be upgraded to a quantum primitive? How many people notice such a primitive in this algorithm? I've used a classic primitive, right? Some people, okay, yeah, so this is this thing. You know, we talked about the success probability amplification thing. If you have an algorithm that succeeds with some small probability, you can just do it 1 over that number of probability times and you'll see it. But you can actually speed this up by using amplitude amplification, right? So in fact, you can. If you additionally use amplitude amplification, you'll only have cost proportion 1 to the square root of probability, which will now be kappa squared. So this kappa squared becomes a kappa, and this kappa remains a kappa. So you'll get kappa squared over epsilon. So many of the linear system algorithms, or maybe all of them, you can always break down into these primitives, which is kind of what I've been saying. This algorithm, for example, uses 3 primitives: phase estimation, Hamiltonian simulation, amplitude amplification. And here's a breakdown of many known quantum linear system solvers in terms of its primitives, just to show you that you can do this in general. So the first algorithm I presented was the kappa cubed over epsilon. The kappa squared over epsilon, this is the problem algorithm that's given in the original Harrow, Hasidim, Lloyd paper. If I use some different, an extra primitive called variable time amplitude amplification, you can get this to kappa over here. So that's pretty cool. If I use another primitive called LCU, this is linear combination of unitaries. I didn't explain what this is, but it's a primitive. And this variable time amplification, you can get even better scaling. The epsilon scaling became a log over here. This is quantum signal processing, also gives you something, and there's many more intermediate things that I was too lazy to write down. But eventually, the best known algorithm uses a discrete adiabatic algorithm and a quantum walk and gets this. And this best known algorithm is in this paper. So all the linear system algorithms, you can view them through the lens of what primitives do they use. And as we upgrade the primitives, get newer and newer primitives, newer as in newer in time, like, you know, these like Hamiltonian simulation and phase estimation are more than 20-year-old primitives. So is amplitude amplification. Variable time amplitude amplification is a newer primitive. It's only, I don't know, 15 years old, 10 years old, something like that. LCU is even more recent. QSP and QSVT are even more recent. So as we add new primitives, you get better algorithms. Okay, cool. That's all I wanted to say about quantum linear system solvers. Maybe I'll pause here for questions. Yeah, there's a question over there. Yes, very good question. Yeah, what about this conditional rotation? So it's efficient in the number of bits that you need, this representation, and I'm only going to need like log 1 over epsilon bits to get epsilon precision. So it's like, I'll get an extra log 1 over epsilon, or maybe poly log 1 over epsilon. But like, I haven't been keeping track of log factors very accurately anyway. So, but it's a log factor, so we don't have to worry about it. That's the short answer. Good question. Yeah, any other questions about linear system solvers? Oh yeah. Exactly. Right. Mm-hmm. That's right. Right. Yeah, that's a good point. So, I mean, of course, like what you call a primitive and what you don't call a primitive is also a matter of taste. But HHL itself can be broken down into more fundamental primitives. But of course, once you have HHL, you can just use HHL as a primitive. You don't have to keep breaking it down to little primitives. So just treat HHL as a black box from now. This one of linear systems problem as a black box, and that's perfectly a reasonable thing to do. And you can add it to your primitive toolbox. Don't have to keep thinking about how it works. But yeah, I wanted to demonstrate how it works in terms of the existing primitives, and that's why I talked about this. And okay, I have 15 minutes left, so what did I want to talk about? I wanted to say, is my clicker not working? Oh, okay, good. So the primitives I did not talk about are block encoding, LCU, quantum signal processing, and quantum singular value transformation. And I thought about talking about them in this talk, but I realized that to do them justice, I would need like an hour or so, which I don't have. So instead, let me point you to, because yeah, I have 15 minutes. Let me point you some good resources. If you're the kind of person who likes lecture notes, there's good lecture notes by Lin Lin that cover all of these 3 things in some detail. Of course, the quantum algorithms lecture notes I talked about, like on slide 1 or something by Andrew Childs, also covers this in some detail. I gave a talk on some of these primitives, not QSVT. My talk predates QSVT. So the first three things, and that's on YouTube here. If you really love the sound of my voice and want to hear me talk about this, you can go click on this link. Well, not really click on it because it's on a screen, but you know what I mean. Anders Gillian, one of the inventors of QSVT, also gave a talk on QSVT. That's over here. But this and Ike Chuang also gave a talk on QSVT. These two are specifically about QSVT. This talk is about the first three, and the lecture notes cover everything. So take your pick. Okay, and finally, good. That brings me to a summary. I also wanted to take a few minutes to tell you about the quantum algorithm talks at this QIP. Maybe this tutorial has inspired you to go learn about quantum algorithms. So I want to tell you what talks are there, what they're talking about. So, but let me just summarize. So instead of giving a long-winded summary of what this talk was about, this is the summary. Right? Hope you remember this meme from earlier. Just no more primitives. That's what I'm saying. Okay, but maybe you're thinking like, how do I put this into practice? This is all mighty well and good as an abstract philosophy, and like I can say this because I'm not a grad student and I don't have to write papers and so on. But you can't put this into practice. And like what I'd say is, when you're reading a new quantum algorithms paper, this, if this clicker works, yeah, how to put this in practice. When you're reading a new quantum algorithms paper, try to identify the primitives. That would be my one takeaway message. Don't just be like, oh, I read 4 quantum algorithms papers this week, but don't count the number of quantum algorithms you understand. Understand the primitives. So how many primitives were there in this quantum algorithm? What were they? Were they classical? Were they quantum? Try to think about the algorithm as a sum of primitives. So like I described the HHL algorithm, you can think as a sum of phase estimation, Hamiltonian simulation, and amplitude amplification. So if you get better and better at this, you'll start seeing that the landscape of quantum algorithms is not as complicated as it seems. There's just a few quantum algorithms. I mean, there's not a few quantum, sorry, there's only a few primitives. There's many quantum algorithms you can build out of these primitives. Yeah, try to see if you can upgrade them, that kind of thing. Just try to get comfortable with these. And yeah, more along these lines of like, I don't know, career advice for grad students or whatever this theme is for the last 2 slides. If you're wondering like, how do you be exposed to more algorithms? How do you learn the correct building blocks for classical randomized, so deterministic randomized and quantum algorithms? This is the guide I would suggest. Of course, everybody might have a different opinion. For grad students, learn the primitives, as I was saying. But how do you do this? You need to learn algorithms. So take an intro course on algorithms. These are some 2 textbooks I would recommend. Take a course on randomized algorithms. Here's a textbook I would recommend instead. So these are either or. You can either take a course or you can read a textbook, whatever you like. And same thing for quantum algorithms. Take a course or read Andrew Child's lecture notes. Cool. Okay. That's the end of the me telling you about stuff part of this talk. I wanted to spend the last few minutes telling you about the quantum algorithm talks at QIP and motivating you to go attend some of these. And I've divided into some areas, like, dividing up a field into different areas is always a matter of taste. This is just like how I've done it. So the first division of the field is quantum query complexity. So we've talked quite a bit about quantum query complexity and friends. And so these are algorithms, the problems that are related to query complexity. I have 10 minutes. Let's see. Maybe I can speed run and tell you one sentence about each of these papers. I was first just going to show you these, what the talks are, but maybe I'll just give you one sentence each. Let's see if I can do that. Okay, first paper gives resolves a long-standing open question in quantum query complexity about the power of a lower bound technique called the polynomial method, and it shows that you can have an exponential separation between the polynomial method and quantum query complexity. Second paper gives a way of doing the quantum divide and conquer, which is a paradigm I talked about a long time ago in this tutorial, and gives you a way to do this efficiently in terms of time complexity. So you should see this. This is a hint to, it might be using the QRAM model. Does it? You'll find out. This is not query complexity. It's streaming algorithms. It's related to query complexity. You have access to input data through a stream, and it gives you an example, or the first example of an exponential quantum advantage in streaming for a natural problem, max directed cut, not a problem that was invented specifically to show this separation. This paper I talked about earlier, it's about efficiently preparing quantum states, using only one query to a classical oracle. The next paper is kind of the similar theme. You want to make classical queries to an oracle, but now instead of creating a quantum state, you want to prepare a unitary. But the message is the opposite. This shows that you cannot do it with one query, whereas this paper says you can do it with one query. This is about quantum query complexity of functions of matrices. So you want to compute some function that can be, and you have query access to the matrix, and it characterizes when you can do this in terms of other complexity measures of the function. This is about the power of adaptivity. Adaptivity is this idea that you can make future queries based on the queries you've already made, the outputs to queries you've already seen. And now this might be better than just making all your queries up front. And in fact, it is better. And this paper gives you, explains the power. Um, Next slide. Okay, there's a lot of papers on this rough theme that I'm calling machine learning and tomography and metrology. The first one solves a question about, can you learn quantum Hamiltonians given copies of the Gibbs state of the Hamiltonian? It shows how to do this at any temperature and polynomial time. The second paper is about learning shallow quantum circuits. So you're given as a black box a quantum circuit that's shallow, it has small depth, and you want to figure out what this quantum circuit is. The next paper is about learning a quantum state in a different metric than is usually studied. It's the chi-squared distance. Usually you might have seen this for the diamond norm or fidelity. This paper is about learning a classical parameter of a quantum state given when there's perturbing interactions. So there's some interactions happening that you don't like, and you still want to learn this thing. Can you still do it? This is quantum metrology in the finite sample regime. This is kind of like developing a theory for quantum metrology that's similar to the PAC model in classical computer science. If you know this, it's called the probabilistic approximately correct model. And this last one, I couldn't find this on the archive, but I'm just going to guess based on the title, which is that you're given copies of some highly entangled state from some special class of states, or you're promised it's far from this, and you want to figure this out, but not by doing some crazy entangled measurement, by just doing some simple few qubit measurements. I hope that was an accurate summary. Okay, next set of talks on this topic. Learning quantum states with respect to the stabilizer formalism was also not on the archive, at least not under this title, but I assume what's going on is you want to learn quantum states that are, if they're stabilizer states, we already know how to learn them, but this is about states that are close to being stabilizer states. Maybe they have some T gates in it or whatever, and you still want to learn them using the same kinds of ideas that are used. This paper is about learning quantum states in the same phase of matter. Right, we're given some example quantum states in the same phase of matter. You want to learn them. There was some previous work on this at a previous QIP. I think these works, it's a merger of two papers, improves on this. These are both barren plateaus papers. So this is quantum machine learning. In quantum machine learning, often what you're doing is trying to train some kind of parameterized quantum circuit, and you take gradients. And you often find that the gradient is zero and you don't know where to move, so gradient descent is stuck. This is called a barren plateau phenomenon, and these two papers tell you more about characterizing when this phenomenon happens. The last paper is about learning unitary channels. So you're given a black box, implements a unitary. You want to write down a classical description that is correct in diamond norm distance. Okay, that's the machine learning algorithms. Good. The third category I want to put stuff into is quantum simulation and linear algebra. The first paper is about a new exponential quantum speedup for a problem that's purely classical, about simulating classical oscillators, or what I like to call balls and springs. The next one is a quantum speedup for approximating the top eigenvector of a matrix. So this was also not on the archive, so I'm just going to make an educated guess that you get a quantum speedup for approximating the top eigenvector of a matrix. Right? It's very self-explanatory. Good title. Next one's about, this is state transformations. You have some quantum state, it has some amplitudes. You want to modify the amplitudes in some way, in some nonlinear way, and this gives you some techniques for doing this. Quantum eigenvalue processing was also not in the archive. Just from the title, I'm going to guess maybe it's related to quantum singular value processing or quantum signal processing. I don't know, I'm just guessing right now. This paper, linear combination of, okay, so this is solving a linear differential equation on a quantum computer by expressing the operator that you want to do as a linear combination of not just any old unitaries, but specifically of Hamiltonian simulation maps. So you express the operator you want as a sum of e to the IHTs for different values of t. Unexpected Trotter error scaling. So Trotter is a way of doing Hamiltonian simulation, and often the theoretical bounds you can prove are not similar to, are way worse than what actually happens, and there's unexpected Trotter scaling. We'll learn more about what that is in this talk. Optimization, right? So this first talk is quantum thermal state preparation. The thermal state, or the Gibbs state, is a state that maybe you want to prepare on your quantum computer, and this gives you some open quantum dynamics type algorithms, Lindblad simulation type algorithms for preparing these thermal states. The next paper is about local minima in quantum systems. Again, you want to minimize the energy of a quantum state with respect to some geometry, and this paper shows it depends on your definition of what you count as local, but under some definitions it's easy, under some definitions it's hard. This is a paper I talked about earlier. It's a no-go result saying that classically, if you want to do non-convex optimization, generally it's hard, it's NP hard, but if you want to find a global minimum. But if you just want to find a stationary point, which is a point where the gradient vanishes, this you can do efficiently with gradient descent. Classically, this paper shows that there's no quantum speedup for that problem. So no quantum speedup over gradient descent. This paper is, it's also one of these titles that totally explains what the result is. Very nice. I love these titles. There's a quantum speedup for linear programming, and it uses interior point methods. Interior point methods are a well-known method for solving linear programs classically. The final category is algebraic problems. The first two papers, I think, are similar. I don't know. Algebraic problems are not my area of expertise, so I hope I don't mess this up. But I think they're both about a mixed Schur transform. The Schur transform is the thing that block diagonalizes the tensor power n tensor power. Like if you have a unitary and take u tensor n, if you want to block diagonalize this operator, you would use a Schur transform. But now, if it's not just u tensor n, but it's u tensor n and the complex conjugate of u tensor m, what do? You use something called the mixed Schur transform, and these two papers give you some efficient quantum circuits for doing that. The last one is about computing Kronecker coefficients. There's some complexity results in here that it's hard, but there's also some algorithm results showing that it's easy. Okay, so I hope this overview of all the talks at QIP was helpful for you. And that is the end of my talk. Thanks for coming to my tutorial. These are all the people who helped me. Thank you so much.